Hi everyone. In this video, we are going to talk about boosting. And in specific, we're going to be talking about gradient boosting, and even getting a little bit more specific, we're going to talk about extreme gradient boosting, or XGBoost. And what boosting is like bagging and pasting and the others we've seen, random patches, is an ensemble learning algorithm that combines a number of weak learners. And as we learned in talking about bagging and pasting, a weak learner is a learner that is slightly better than chance. So when we're looking at these pictures and trying to decide whether it's a cat or not, or distinguishing between a cat and a dog, slightly better than chance might be 60%. So we're 60% accurate in seeing pictures of cats. When looking at that clothing example, when there were 10 categories, slightly better than chance might be 20%. So slightly better than chance seems like, well, it must be better than 50%, but it depends on what we're categorizing. So that's what weak learning is, what a weak learner is. So in boosting, we're combining a number of weak learners to create what's called, at least the hope is that we can combine these weak learners to create a strong one with some arbitrary definition of what is meant by good performance, right? We want something that performs well. That's kind of the strong learner. And again, we determined that that was a little vague in what that meant. So in the dog cat, we were hoping for near zero error, but in looking at far away pictures of people and deciding whether they are women or not, maybe we could tolerate 10% error, and that would be good performance. This is from the documentation of XGBoost, and so the idea here is that we're combining a number of trees, decision trees, stubs, or at least very low-depth decision trees, and we're combining them in a certain way. So we have tree 1 there, we're saying is the age smaller than 15, and another question is the person male, and tree 2 was, do they use the computer daily? And if we're trying to decide whether that person is that young boy, we would take the 2 from the tree 1, so the +2, and that +9 or +0.9 from tree 2, and combine them to get a score of 2.9. And if we're trying to decide instead if that person is that older man with the mustache, we're combining that -1 from tree 1 and that -0.9 from tree 2 to get -1.9. So in this case, in this very small ensemble, we'd say the likelihood is that it's that small young boy. And imagine this, that we have all this training data, that's that white egg, and we extract some to train the first classifier, and that classifier makes mistakes, and that darker blue represents the mistakes that classifier makes. So when we're training classifier 2, we're going to include or favor those instances that are mistakes from classifier 1. So we're going to make sure that those mistakes made by classifier 1 are part of the training data for classifier 2. And so on. So the mistakes that next classifier makes will be used as instances for training for the next classifier. So we're training on the errors of the previous classifier. And note that this is different from when we did bagging and pasting. Everything was pretty independent, right? We didn't rely on mistakes that other ones made. We just kind of took some random sample of the training data and trained our classifiers. And we're calling those mistakes the first classifier makes, or errors the first classifier makes, or any classifier, the residual. That's what's left over after that classifier makes some estimation. So the residual then is used in some way to train the next classifier. And the example I like to use is one-dimensional team frisbee golf. So the task is that we have that hole there, that circle on the right, that white circle, and the frisbee is the orange circle on the left. And we have a team of people, and the first person to go, let's say Anne, takes a look at that line, has some vision of that circle, the goal, and says, I don't know, that looks like 80 feet, and flings that frisbee. And it ends up there. So that's the result. Now the next person, let's say Ben, takes a look. Notice that Ben isn't looking way back at that original spot on the left, but now he's working with the residual. So we're calling that difference the residual. So Ben takes a look at that, thinks that looks like, I don't know, 10 feet, and flings the frisbee and gets there. Now it's Clara's turn on the team. And she takes a look at that and thinks that looks like about 20 difference from the whole. So she's going to fling it 20. So that's the residual that she's looking at. She's dealing with the residual. She's not dealing with the original problem of starting with the Frisbee way on the left, right? She's working with what's left over after these previous people went. That's a residual. So she flings it 20 and gets there. Now it's, Dan's turn. And he looks at it and says that looks around 10 feet. So that's the residual. And flings it and makes the hole. So that's 1D team Frisbee golf. And the idea here is that all these different people on the team aren't working with the same original problem. Only the first person is. And then each person after that's working on that residual or what's left of the problem. So recently my dog Roz, that's the dog in the front seat there, my truck, got sick. And so I took her to the vet. And you can think of the vet's expertise as this white egg again. Right? So that vet has some expertise. But the vet isn't perfect, right? And lacks some information, and that's represented there. And so if I was unsure that the vet was accurate in the diagnosis of Roz, I might go seek other vets. And that kind of goes back to the bagging and pasting example of if we just keep getting consults to other vets, maybe we'll reduce that error and we're likely to do it. But going back to that original vet, it's like these errors are kind of all over, right? That the vet has lots of knowledge, but there's some gaps in the knowledge. And so we might want to see some experts that have deeper knowledge in one area, like a cardiologist or an oncologist, or in my case, I took Roz to the neurologist. So these specialty people have knowledge that isn't present in that whole. So they're sort of working on those residuals too. So much so that when we asked the neurologist another question about the dog dealing with some possible cancer issues on her foot, she just said, that's not in my wheelhouse. So that's a case where the neurologist is an expert in everything, isn't the whole big egg, but is only an expert in that residual, the things that are normally missing from the general practitioner vet. I don't know what you call that general practitioner vet. Right? And there might be some expertise there in the neurology department that the neurologist may not know, and maybe there's a research university that has experts on that particular issue. So it kind of keeps going down. That then is another residual. Typical neurologists don't know this, but there are specialized places in the country, perhaps, that have this expertise. So that's what boosting is. It's working on these residuals, and XGBoost is called Extreme Gradient Boosting. And it offers state-of-the-art performance. So other than deep learning, which we're transferring to shortly, it's really the algorithm that'll get you the farthest. So kind of people have said, when in doubt, use XGBoost. And it's very fast compared to other things. It's written in C++. That was the original implementation. And now it has a lot of APIs for languages. In our case, it has an API for Python, but there's also like Julia, Java. So you can use XGBoost and the tremendous speed it has with a simple interface in the language of your choice. The other thing that's important is that it's parallelizable. So not only can we use it just on a CPU, that'd be a bit slow, but we can also use the power of a GPU, and we can even spread it across multiple machines. So that's really handy that we can parallelize this and speed it up. And not only is it good for one type of problem like classification, but it also can be used for regression. So it's sort of multi-purpose there. So if you're trying to do a classification problem or a regression one, XGBoost is a good option for both those. The other thing is, a lot of times when we've been working with other algorithms, we had to clean the data to get rid of missing values because we'd be getting these errors. But XGBoost handles missing values fine, so we don't have to worry so much about cleaning and altering the data set. So that's a big advantage. XGBoost has a number of hyperparameters to adjust, so to improve performance. And there's many of them. I'm not going to cover all of them here, but some of them are what the objective is. So we can have a softmax problem, which is we're just interested in knowing what the classification is, which of the 10 possible closing choices is it. And multi-soft prob is give me the probabilities for all these. So there's a number of objectives one can use. There's this eta, which is the learning rate that we can adjust. By default, it's 0.3, but some people lower it to 0.2 or 0.1. The max depth we've seen before, so that's the depth of the trees, and many others. XGBoost is a pretty impressive algorithm, and it just doesn't rely on this max depth factor, but also kind of prunes the tree to make them as efficient as possible. So that's kind of a big factor of XGBoost. So it's time for a quick demo of XGBoost. So let's do it. All right, so here I am at my demo. And the first thing you notice is that I'm running on a GPU. Let's just double check to see that's true. And yes, it is. So I'm using a GPU accelerator. And I'll just double check what I have here. It always takes a little bit of time to start these Python notebooks. And there we go. It's that Tesla K80 again. And the example I'm going to use is that one we've used before, which is the clothing example. So I have all these images of clothing, 60,000 of them, and we're going to see if we can identify them. And here's all the stuff I've showed you before in previous videos. And we get those pictures. So we've loaded the data. And now I'm going to divide it up as we did before as well. So this is all, I'm not going to explain everything because we explained it before. All right, so finally we can get into XGBoost, and instead of typing these, I thought for this video, I'll just show you what I did here. So the first line is I need to import that XGBoost classifier, which I do. And then XGBoost classifier requires a parameter list as a Python dictionary. So I have those there. I'm going to make one that has 200 classifiers. That eta, the learning rate is 0.2. I'm using this GPU hist, which is using the GPU to construct the learning algorithm or to do training. The predictor is also going to use a GPU, and I'm going to limit the depth of the tree to 20. So let's go ahead and do that. And now I'm going to fit the model on the training data. So remember that when we first did this, I think it took 12 minutes or something on bagging, and this looks like it'd be horrendously slow because with bagging, we can train those classifiers in parallel, right? There's no dependency among classifiers. Here there is a dependency because one classifier is going to work on the residual of the previous classifier. So you'd think this would be way slow, but as I mentioned in the slides, XGBoost is really optimized for speed. It's written in C++. It can be parallelized. So this is actually going to be fairly quick. Let's see. Well, let's time it actually. Yep. Okay, and that took a lot longer than usual. I think it's the weekend traffic maybe, I'm not sure, but it took 6 minutes and 47 seconds to train 200 models, so that's pretty good. Let's take a look at the predictions. And let's get the accuracy here. So significantly better than bagging and pasting. I think we had around 87 point something % accuracy, and now we're at 89.69. So that's just a quick demo of XGBoost. The Python Jupyter notebooks have more information. Thanks so much for watching. Take care. Bye.